Hi class, Miss Lee signing in. Just to continue on where we left off last class on the examples from tension. Some of the key points before we start. Last class we did a couple examples with tension. Some of the key things to note are that when we have a system of two objects tied with a string, one of the key points was your masses have the same acceleration, so that when you wanted to calculate for acceleration or use acceleration, you could have done that for either cart. Another key thing that we looked at last class was your tension force canceled in your F net equation if you used both masses as your system, like you see over here. Using both masses allows both tension forces to cancel, which then allowed you to solve for the acceleration. So we're going to continue with this example down here with tension in the string in your Atwood's machine. We didn't get a chance to finish this question. We did find the acceleration of your entire system down on the left side here. So what I'll do is I will do the solution for, I will do the solution for M2 and M1 as well. So what I'll do is I'll divide this here in half, and for mass 2, we're just going to write the F net equation. We now know the acceleration, which then we can put into our equation here. So we have F net is equal to, and my direction of acceleration I will use is downwards. So the force that's pointing in line with the acceleration is Fg2, and the force that counters that acting on this mass is Ft, the tension force. And this is equal to mass 2 times acceleration. And looking at our F net equation, I know that Fg is mg minus Ft equals m2a. And to solve for Ft, I am going to put Ft on the other side to make it positive, which then gives me m2g equals m2a plus Ft. And I'm going to move the m2a over to solve for Ft. So minus m2a minus m2a. And this gives us, and I'm going to rearrange, I'm just going to put t on this other side so it looks more linear. So I have Ft is equal to m2g minus m2a. And putting everything in, I have mass of 2 is 6 kilograms times 9.81. I'm running out of space, so I didn't put in units, times the acceleration, which now we know is 2.2. It's I think it's 1.9 something, but for the sake of technique, it's better to round it, but I'm just showing you this example. When you're doing questions, you should always round until the don't round until the last step. So you put this one in, and it looks like this is going to give you about 40 something newtons, but we can confirm that with the calculation. So we get 46.86. That's going to round up to about 47 newtons. Okay, so I'm going to do the same thing, but for M1 on the other side. So I'm just going to solve it using very similar methods to what I did for M2, and I will just show the solution on the board if that's what you did as well. So here I've done the same example with mass 1. Notice the answers are slightly different, and the reason why is because I used a rounded answer for acceleration. Ideally, I would have used a non-rounded value for acceleration, and the tension forces should have turned out to be exactly the same number. But after rounding, they're roughly about 47 newtons. So just to speed things up, I wanted to just, ideally, you don't want to do that in your question. You want to use the original value as close as you can. Okay, so here we've done the example for Atwoods. You should be able to do all the questions on the first page of your worksheet, or at least you should be able to attempt them. And but I want to show you one other case where instead of having both your masses hang off from a pulley and the pulley redirecting the force, we're going to do something similar in which we're going to loop one of the masses around a pulley. One's going to dangle off the table here. The other one we're going to put on the table. This is going to be related to the lab that we're doing. So in terms of a free body diagram, make sure you know how to draw one of these. I'm going to go over example 3 as well as example 4. I've asked, let's give this one a shot here. And here, luckily, we're going to assume the table is frictionless. And example 4, there will be some friction to deal with. So let's start with our free body diagram. As you guessed, there will be friction acting on both. Actually, there's gravity acting on both of these bodies. So let's draw both of these in. I'm going to call this guy mass 1 and this guy mass 2. And starting with the gravity forces acting on these, here they are. Now on mass 1, we have this tension force of tension, and then same over here, force of tension acting on mass 2. Now notice, again, like before, the tension forces always start from the object, from each end, and point towards the center of the string. And they're equal and opposite in direction, along the line of acceleration. For the F2 mass, we also have Fn. And keep in mind, there is no Fn for M1. And think about the reason. Yes, you've guessed it. It is because there's no surface M1 is in contact with. Please do not draw Fn paired with every Fg, because that's not always the case. Fn is only if you have a surface that your object is in contact with. Since there's no friction force acting on M2, we don't have to draw that one in. This is our completed free body diagram. We're going to need this free body diagram to figure out the acceleration of the masses. Now, the process is very similar. For the acceleration of the masses, we are going to want to use the entire system to help us figure the acceleration, because notice that in either case of these masses, we don't know the tension force, and not knowing the tension force means we're not going to be able to find the acceleration if we use either system as for our F-net equation. Keep in mind, in this example, our acceleration is around the pulley. Just like in our last one, our acceleration is on a pulley down from the other side, but this case, it's horizontal and then vertical instead of vertical and then vertical down on the other side. So this is the difference here. And so for acceleration, this is going to be our line of acceleration right there. So we're going to consider only the forces along that line if we're in our F-net equation. So our F-net along the line, that black line, we have Fg1 along that line. We have Ft moving back against the line, the purple Ft in line, and that's it. There's no friction force, 1, 2, 3 forces along that line, and this is going to be equal to, and notice I've used the entire system, which is mass 1 and the mass 2 included, times the acceleration. These Ft's cancel, so I am left with Fg1 is equal to mass 1 plus mass 2 times the acceleration of our system. And then I just have to divide both sides by mass 1 and mass 2 to solve for acceleration. we get acceleration is fg1 over m1 plus m2. And to solve for an fg1, that's going to be m1g divided by m1 plus m2. And that's going to give us mass of 1 over here is our 6 kilograms times 9.81 divided by 8 kilograms plus 6 kilograms. And that's going to give us 6 times 9.81. Oh, I forgot the 1 there. And divided by, well, at the bottom, the total 8 plus 6 is 14. So divided by 14, which gives us 4.2. 4.2 meters per second squared down on the right. That's the direction of our acceleration. And I'm actually going to store this number on my calculator so it can come in handy later. Okay, so I have found the acceleration for both mass 1 and mass 2. The next step is to find the tension in the rope. Notice that in finding the acceleration, Fg1 was the only force responsible for pulling both masses together. And it's not just pulling mg1 by itself, it's pulling both these masses. As a result, you get an acceleration that's less than 9.81. Because if you imagine if you cut the string right there, then this object, this 6 kilogram mass, which will fall, the acceleration of that would be 9.81. But now it has to drag another mass across the table. Now, luckily, it doesn't have any friction to counter, which then would further decrease acceleration. It only has to drag the one mass, increasing the inertia of your system, which then, as a result, you won't get as much acceleration as 9.81. You get something less, 4.2. And that's because you're dragging both masses, and you only have one of the FGs. You'll have one of the forces of gravity, only the weights of one mass to pull this one down. So this is kind of what this kind of how this works. Okay, so at this point, I would say it is a good time to try 3B, and pause this video. If I've gone too fast, you can go back, rewind, replay some parts to if you missed some of the notes, or if you didn't get certain parts, if I've talked too fast, you can go back and rewind there. Otherwise, here's a chance to pause before I go on to 3B. After that, I'm going to do that for question 4. And if for question 4, maybe that's a question you can work at your own pace and watch the video by yourself to do that one. Here's your chance to pause. Okay, I will continue with 3B. So, and just like the questions before, I'm going to divide this between M1 and M2. I will solve for both. So I have for M1, I have F net for M1, and using the black line, the line of acceleration, I have going down on the right, I have Fg1 minus the tension force, and this is equal to my M1 times the acceleration. Now I'm going to solve for the tension force. I'm going to move it to the other side. And after I do that, I'm going to have Fg1 equals M1A plus Ft. And moving M1A to the other side. At this point, it just becomes algebra. You can do this. Fg1 minus M1A equals to Ft. And I'm going to do a switcheroo between the left and right of my equations. I get Fg1 minus M1A. I'm going to zoom in now. which then Fg is just mass times gravity. And I know my acceleration of m1, this was what I found previously in question 3a. Putting this one in, my mass 1 is 6 kilograms. 6 kilograms times gravity, 9.81, minus 6 kilograms times 4.2. And of course, I'm going to use the non-rounded version from my calculator. Hopefully, I've stored it up as Z. So I will do 6 times Z minus, oops, nope, that's wrong. 6 times 9.81 minus 6 times Z, giving us 33.63. 33.63 dot dot dot, which rounds up to 3.4 newtons. Okay, and on the other side, M2. M2, I get F net. And F2 is actually a lot easier, to be honest. It really doesn't matter which one you choose. Try to pick the easier one. Give yourself a break, you know. So here we'll have one force along the line of the acceleration in black, which is Ft, equals to m2a. Yeah, it's a lot easier, right? So if we put in the m2, that's going to be 8 kilograms times our acceleration, 4.2 meters per second squared. I have space now, so I'm putting in the units. And I'm going to put 8, and I'm going to times our acceleration, which is, stored it in Z, which again, 33.63. Notice if I use exactly the non-rounded version, I get consistent answers for both. So 33.63, which rounds up to 34 newtons. Bam. Okay? Doesn't matter which way you solved it, but as long as you're consistent with the line of acceleration and the direction of the forces in relation to the acceleration, you'll have no problem. Okay, so at this point, we're on question 4, and the only difference here is we have friction force. Again, I think that if you should give example 4 a try. At the very least, if you feel you can't, if you think you're going to struggle with drawing the free body diagram, watch me draw the free body diagram, try out the problem. It's almost exactly the same as example 3, except you got one extra force in your F net equation. Otherwise, this is a good, if you want me to go over afterwards, pause the video, try the example, and then come back and watch the video if you feel like you need some help. Here's a chance to pause. Okay, so let's start off. Example 4. Again, I'm going to label this as mass 2, label this as mass 1. And I'm going to draw the free body diagram. The only difference in this problem is we're given the friction force. Now, if you were really savvy, what you could do is for question C, you could find coefficient of kinetic friction. If you want that as a challenge problem, you could also find what would be the and for another challenge problem, you can even find what would you need, what minimum coefficient of static friction you would need for your entire system not to move at all, to accelerate at all, essentially. So that could be another challenge problem you can try for D if you want. I'll write it down. You're finding minimum coefficient of static friction for acceleration to be 0, essentially, for your object to not move. Anyways, I won't go over those, but I will, if you want me to, we can go over next class when you come back if you want to. Those are some questions I thought on the spot you can think about. Anyways, let's draw our free body diagram. We have Fg1 here. We have the tension force pulling, keeping this guy in check. And of course, this tension force is caused by this mass 2 lagging behind, which then will make the rope tense. Okay, and of course, we have Fg2 acting on the 8 kilogram mass. We have the normal force just like before, and what's different now, it's the direction of the friction. It's the friction force acting on the 8 kilogram mass. And for this guy, because this object is going to move along this line of acceleration, the friction force is going to counter that. So friction is backwards from the line of acceleration. And that's the only difference between this free body diagram and the previous free body diagram. We're going to do exactly the same as we did in the last problem, which is consider the system as a whole when we're solving for the acceleration of the masses. And also like the previous problem, this is different from the previous problem. Friction is going to hinder your two objects accelerating down on the right. So our acceleration should be less than 4.2. If we get a number that's larger than 4.2, we know there's something wrong with how we set up our problem. That's always a good way to double check your answer. So with our acceleration of our masses, we will go ahead and proceed with our F-net equation. So our F-net is going to be along this line of acceleration, Fg1 minus Ft. Oh, I should have used this color. Fg1 minus Ft counter in the opposite direction of acceleration, plus the other Ft with is in line in the direction of acceleration. Now what's different here is now we have a friction force, and a friction force opposes the direction of our acceleration. So that's going to be a minus here, which is going to be equal to mass 1 and 2 times the acceleration. Ft's cancel. And we're left with, zooming in here, we're left with Fg1 minus the friction force acting on M2 equals to mass 1 plus mass 2 times the acceleration, which I should have done in blue. Okay. So again, to solve for acceleration, we're just going to divide both sides by M1 and M2. So get rid of this. And this gives us the acceleration is Fg1 minus force of friction divided by the sum of our masses. Fg1, that becomes m1g minus force of friction divided by m1 plus m2. M1 we have as, 6 kilograms times 9.81. I'm running out of space. And our friction force is 25 newtons, as stated in our problem, divided by both masses, the 8 kilogram and the 6 kilogram. Solving for this, we get 6 times 9.81 minus 25 divided by the sum of these two, which is 14. 8 plus 6 is 14. Our acceleration is 2.418, etc. 2.418, rounds up to 2.4 meters per second squared down on the right. And this is nice to know because it is less than 4.2, which is great. It follows it checks out because now we have friction. We expect our acceleration of our system to be lower. I'm going to quickly store this number. Done. Okay. Now, if you're watching this video still, I would say this is a good time to pause again and try tension. If you were stuck on A, maybe it's a good time to find tension in the rope. Here's a chance to pause. Okay, coming back. So, like the previous problems, again, I will do both solutions. And I will do one for M1, one for M2. Let's start with M1. Notice in this case, using either mass is going to give you a complex thing to work with, so it doesn't really matter. Anyways, our F net here is going to be down on the right of our acceleration. We have Fg1 minus our Ft is equal to our M1 times our acceleration. And solving for t, we're going to need to move t to the other side and swap over with the M1a. This is getting quite the repetition. Fg is then equal to M1a plus Ft, moving M1a over to the other side. We get Ft, and again I'm going to do a switcheroo here. Ft is going to be Fg1 minus M1a, and Fg1 is just mass times gravity minus M1a. M1 is, I believe, 6 kilograms. 6 kilograms times 9.81 meters per second minus 6 kilograms times our acceleration in our problem that we found from A, 2.4. And after we put this one in, and again, I'm going to use the non-rounded version of our acceleration, which I saved in my calculator. I get 44.34 ... Whoops, 44.34 ... 44 newtons. Now this is interesting because notice this tension force is greater than that in the previous question. It kind of makes sense because if you imagine that you have a block that is kind of it's experiencing friction, it's kind of resisting the motion more down on the right, and because of that you have more resistance, the tension in the rope is going to be a lot greater. So it kind of makes sense that we have a larger tension force in question 4 than in back in 3. There's another way to check your answer. You expect the tension to kind of go up because you're dragging not just a mass, but a mass experiencing friction. So again, for M2, hopefully we should get a very similar value. So I'm zooming in to M2. I wanted to say something and I totally forgot what it was. Okay, if I remember, I'll come back. Okay, so we have F net here, and then we have, oh yes, looking at M2, we have Ft pulling it forward, but now we have friction resisting that. So I have to subtract friction equals M2a, and I'm going to put Ft on the FF on the other side. The algebra for M2 just always seems a lot easier. So the more you do these problems, you'll find kind of little tricks and easier ways to make your life a lot easier. Okay, so we have M2a. We have M2, which is 8 times our acceleration, 2.4. And plus our friction force, and 8 times our acceleration plus 25, which should give us exactly 40.3485. That was exactly the same if you used the non-rounded value for your acceleration. So we got 44.34 dot dot dot, which rounds up to 44 newtons. Bam. Okay. So here we have the tension. Oh, I remember what I was going to say. And that, some problems could be, you can think about it. Notice that depending on your situation, tension in your string increases. And if sometimes there's a maximum limit on the tension in your string before it breaks. So there's questions that might involve that one as well. Same for also for C and D. If you want to give that one a try, which you can, you have the friction force of 25 newtons. You could use M1 to figure out what the coefficient kinetic friction is. And if you also want to, you can even try to find what would your minimum coefficient static friction needed for your whole system to not accelerate. This is a bit trickier. And my hint for that one is the friction force is not 25 newtons. That's not the case. Because, of course, we're not only dealing with static friction, we pretty much want to find out what is the force that you need to completely oppose the force that's causing your system to accelerate down on the right. So here is all of the examples. Again, feel free to play the video. Thank you for bearing with all of these examples and my writing and my terrible voice right now. But anyways, next class we will maybe have a chance to go over some of these if you want to ask more questions. But hopefully you can now do all the problems on your worksheet and give them at least a try. So thank you again for watching, and I will see you next time on the Lead Channel. Signing out.